Hello, everyone, and welcome to another Mirage Talk. My name is Eli Tiomkin, and I will be your host today. Today we have an interesting speaker, Doug. Doug Fink. I actually know Doug for many years, working in the same company in the storage and memory market. Doug is today the Chief Content Officer for Global Quantum Intelligence. And Doug will share a talk with us about quantum computers. Doug, the stage is yours.
Okay, thank you, Ellie. Well, let me bring up my presentation and we'll get started. Okay, hopefully everyone, you can all see this presentation. I'm going to talk about what's happening today in quantum computing and when it will happen. And my firm again is Global Quantum Intelligence. We are the leading business intelligence firm. We started actually in 2015 with a predecessor company, which I started called the Quantum Computing Report. So we've been working at this area for almost 9 years now. So we know a lot. I'm going to start with a very high level introduction to the technology. This is a very technical type area, but I'll just give you a high level introduction to it. And it really starts 100 years ago in the early 20th century. There was really a revolution in physics, which was the discovery of quantum mechanics. You know, a lot of things about physics, even stuff, of course, that we use today, like Ohm's law, electrons, Gauss's law, Boolean algebra, all that was discovered in the 18th or 19th century. And in fact, with the exception of some of the semiconductor technology that's used today, modern computers are primarily based on these old concepts of physics. But again, 100 years ago, people started saying that there were certain phenomena that they theorized and they ultimately proved was available. And even to this day, at least the classical computers we have, even the cell phones, don't utilize them. And some of those concepts, they're not intuitive. Um, I'll talk about them in a little bit more detail: superposition, entanglement, and interference. And a very famous professor, Professor Richard Feynman, who was actually at Caltech, he had a very famous quote, which says, "If you think you understand quantum mechanics, you don't understand quantum mechanics," because things are very, very strange here. And I'll very, very briefly describe these phenomena. The first one is called superposition. Normally when we think of classical computers, you think of bits, and bits are in 0 or 1 at the same time. But in quantum mechanics, you have qubits, which I'll talk about in just a few minutes. Qubits can actually be in what's called a superposition of the 0 and 1 state, or a mixture of the 0 and 1 state at the same time. And they have
Doug, are
very.
are you moving your slides because you're still on the first one?
I am still on the first one.
Okay. Yeah. Yeah. It's not in presenter mode. It's we see
Okay,
the
let me fix something here.
okay.
Um, okay, did you see the one with the coins?
Uh, no, we still see the
Okay,
initial
I'll flip
slide,
that.
the first slide, and then on the side all the other slides.
Okay, what do you see now? You see the one with the coins now?
Oh, yes. Now I see the
Okay,
coin.
I'm gonna have to not use the presenter mode on this,
It's
but
okay. Okay. Sure.
I'll do it like this.
Okay.
mm,
Please continue.
okay. Anyway, so going back here, This is the first thing. This is Richard Feynman. Again, if you don't understand quantum mechanics, or if you think you understand quantum mechanics, you don't understand. Superposition is a very non-intuitive thing. Again, you can have these qubits, which can be in 0 or 1 state, or a mixture of them uh, at the same time. Entanglement is very strange. You can take two qubits, two particles, and they can be entangled such that they are either always in the same state or also in the opposite state, and they can switch at the same time. Albert Einstein called this spooky action at a distance. It can be used for things like quantum key distribution. Some people would say that you can use this for communication faster than the speed of light, but actually that's not the case for various reasons. Uh, be, because because random bits are not equal to useful data. But entanglement, it can be used very effectively for computations, which I'll talk about in just a second. And then the last thing is interference. You can have write an algorithm such that you can have interference. And the famous experiment that proved interference is called the uh, dual slit experiment, where you could take a light or some photons, you can shine them through a single split thing, and you'll get the view that's shown on the right with the light and dark segments there, which is very non-intuitive, but that proves that light is actually can be composed of waves instead of just particles. So how I was saying that, the analogy of a classical bit is called a qubit. It's a quantum bit. It is the basic unit of quantum information. And but they're all a little bit different. As I said, they can be not only in a superposition of 0 and 1 state at the same time, but quantum bits can also have not only that magnitude, but also a phase. And famous professor Erwin Schrödinger had something called postulated something called Schrodinger's cat, just as a thought experiment of how this might work, where you put a cat in a box, and that vial is some type of poison, arsenic or something, and that vial is broken on a random basis by a radioactive decay, which is shown in the box in the upper right. And when the box is closed, that cat is sort of in that superposition. You don't know if the cat is alive or if the cat is dead, as shown in the picture. But then when you open the box, it'll be in one state. It'll be alive or dead. And a qubit is like that also. A qubit, as I said, can be in the superposition of 0 or 1. But if you perform what's called a measurement of that qubit state, then it will collapse. It'll collapse to one or the other. So it's a very unusual phenomena. Again, non-intuitive, but also qubits are very, very fragile. Their lifetime, you can put it in that superposition state, and the lifetime of that can last, depending on the technology, it can last a few milliseconds, or it can last maybe a few seconds, but eventually those qubits will what's called decohere, and again, collapse to one of the states. So the qubits are very sensitive to the external environment. Many of the implementation technologies that I'll show you in just a second will put the qubits in a vacuum, and they'll also put it in a very, very low temperature environment using special refrigerators. Another thing about qubits that make them unusual is that you can't copy a qubit. It's called the no cloning theorem. So, in a classical computer, copying data, of course, is used all the time. You can't quite do it the same way when you have qubits. So it does present some unique challenges, but again, the quantum scientists, quantum physicists have figured out a way around these. So you can implement the qubits in many, many ways. Um, as you can see here, um, you can have them as what's called a trapped ion. You can An ion, of course, is an atom that has, let's say, an electron removed, so it has a charge. You can have a neutral atom which doesn't have charge. You can do it through photonics. You can do it through what's called diamond vacancy. You can have a lattice of carbon atoms, and then you inject occasional nitrogen atoms, which will upset the lattice and create what's called a nitrogen vacancy. Um, you can have superconducting circuits, which are circuits that use Josephson junction at a very, very low temperature. You can have silicon qubits, which are just electrons that are in a semiconductor device. And the most advanced one is called topological qubits, which use a special particle called the Majorana, which you can implement qubits by how you braid them. So that's being investigated by Microsoft. So many different ways of implementing these, these quantum qubits. For some of them, the way that you put them in is an environment that is using a very special refrigerator called a dilution refrigerator, which will cool these down to very, very low temperatures, roughly in the range of 15 millikelvin. And 15 millikelvin is almost about 180 times colder than outer space. So these refrigerators are very, very exotic. They cost upwards of $500,000 each. Um, but the environment is very, very well protected. It's protected against vibration and vacuum, magnetic fields, RF fields. And again, you want to minimize any of the effects of the external environment, because if you do have a lot of things that upset the qubit, it'll decohere, and you could lose your calculation if it decoheres too quickly. So this is an example of these dilution refrigerators and some of the magnetic shielding that some engineers from IBM are putting around. They can be packaged in a box. On the left is a picture of some systems from a company called D-Wave, based in Vancouver, Canada. That's and inside those black boxes are these dilution refrigerators. On the right is an example of a chip. You can some of these are built with chips using semiconductor manufacturing, and a lot of people have hopes that they can leverage the manufacturing capabilities that semiconductors have. So the many ways of building these, but let me talk a little bit about why people have gone to all the trouble to create these and to be able to uh, produce these quantum computers. It turns out that in computer science, there are many, many problems where the computer scientists know theoretically how they can solve the problem, but to process the algorithm that will solve it can take millions and billions of years. And the classical one, this is one that's taught in all basic computer science programs, is called the traveling salesman problem. And the objective of the traveling salesman problem is that you have the salesman, shown a little picture on the right, and you give him a list of cities to travel throughout an area like the United States. And what he wants to do is figure out the path, the order that he should visit those cities that would take the least amount of miles. Since he's driving his car, he wants to minimize the number of miles. And if it's a small number, and it turns out that a number of possible paths is n factorial. So if it's a small number, like if it's 4 cities that he has to visit, he only has to look at 4 factorial, which would be 4 times 3 times 2, which would be 24 paths. If it's 5 cities, it's 5 times 4 times 3 times 2. And it turns out that that number increases very, very rapidly. If you have 100 cities that you give him to the list and he has to analyze each of those 100 has to analyze each of those 100 paths to figure out how long it takes, it's 100 factorial, and that would take millions of years for the very fastest supercomputer. So what you want to do for quantum computing is you want to see if you can solve some of those really, really tough problems. And quantum computer, many problems aren't that tough. So quantum computers will never replace classical computers. In fact, quantum computers will be used in conjunction with classical computers. But there are a lot of problems where that makes sense. And to show you sort of graphically how that works, quantum classical computer scientists will look at a specific quantum algorithm and they'll they'll call it what's called quantum complexity. How does the time to solve the problem increase as you increase the problem size? And again, if you look at this black curve shows that as the problem increases, the time will increase exponentially, or even factorial is even higher. So what they can do, though, is they have found certain algorithms, such as factoring a prime number, where you can come up with a quantum algorithm where the curve is not as steep, and that's shown by the yellow curve in this graph. And at some point, at a certain crossover size, you'll find that the time it takes to solve it with a quantum computer is faster, and in some cases much, much faster than the classical solution. So a lot of the problems that I'll show in some of the next slides are ones where the quantum computer can take some of these problems that would take supercomputers millions or trillions of years to solve, and they can solve it in minutes or hours. And that's where quantum really has the advantage. And there are a lot of very, very important problems that that if they can be solved would have a huge payoff. And that's why people are investing a lot of money into quantum. And I'll talk about some of those applications now. So first, I would point out that the size of the global gross domestic product of the world in 2021 was about $95 trillion, so very, very large. And we have a chart here where we've actually segmented that into all sorts of different areas. There's certainly services, there's industrial, there's what's called primary. And those little icons that you see in those areas show where we think quantum computing can be applicable. They can be applicable for things like optimization. They can be applicable things for sensors. They can be applicable for things like quantum machine learning, as well as chemical simulation. But just about almost all industries can have some utilization of quantum computing or quantum technology in one form or the other. And let's dive a little bit deeper into that. So one of the big areas, and one of the big area that we see as a big potential, is what's called computational chemistry. How can we simulate chemical reactions so that we can predict how two elements or how two molecules will react with each other without actually having to put them in a test tube. That could that could be a big advantage, which I'll talk about in a second. Uh, Quantum machine learning, of course, we all know that AI and machine learning is very hot right now. Um, Quantum has the ability to accelerate some of those and take some of those problems, which may still be intractable for some of the classical machine learning that we do today, and can be done with quantum. Finance is a big area. In finance, you can have a big payoff. Logistics can also be big to reduce the time it takes to do something, or the cost it takes to do something, or the resources it takes to do something. Drug design, sort of a branch of computational chemistry. Uh, it takes over $1 billion to introduce a new drug. Pharmaceutical companies will typically invest over $1 billion and take over 10 years to come up with that new drug. That's because you have to do a lot of empirical testing in the lab, as well as testing with human subjects. Cybersecurity and code breaking is important, which I'll talk about, as well as things like system fault simulation. In terms of computational chemistry, one of the analogies I would use is that you hear, from companies like NVIDIA and Intel and others, they develop these microprocessors that have 100 billion transistors. And you ask, how can they design that and get it right? Because human engineers make mistakes. And even if they make a mistake, let's say every one mistake for every million transistors, when you have 100 billion transistors and you have to fabricate each one over and over and over again, you'll never get it out. And the way they solve that problem is with simulating those transistors in a computer. But up until recently, chemists couldn't do that. Even a 10 atom molecule, something like a caffeine molecule or something like that, um, they could not simulate that because of the fact that the attraction of the electrons and the neutrons and the protons in the molecule, it scales exponentially with size, and it scales, and the attractions have to be described quantum mechanically. So again, Richard Feynman, who I referred to earlier, had a very famous quote, which I'll have here, where he says, "Nature isn't classical, damn it. And if you want to simulate nature, you better make it quantum mechanical." And it's a wonderful problem, but it's not so easy. So people have been thinking about this ever since he suggested that in the early 1980s. For many years, it was in the province of academic researchers and theoretical, but now it's becoming a reality. So there are many, many high value problems that you could solve if you can do a good chemical simulation. One of the ones that I would point out is, how do you make ammonia fertilizer? You may not think that fertilizer actually is very, very important for food production. We would not be able to support the population we have today if we didn't have a good way of creating fertilizer, specifically ammonia fertilizer. But the process that's used today is called the Haber-Bosch process, which takes nitrogen and some other carbon and other things, and it puts them in a vat and submits them to very, very high pressure, very, very high temperature. It turns out that Haber-Bosch processor takes somewhere between 2 to 4% of all the natural gas produced in the world. So we believe there could be a way of doing that much, much more efficiently. And people are trying to use quantum mechanic simulation to be able to find that way. And that could have a tremendous impact on the environment because you wouldn't need as much natural gas, and have, of course, a huge impact on the cost of that fertilizer. High temperature superconductors are something. Automobile companies are looking at trying to improve battery chemistry by simulating the chemistry of the battery with quantum computers for higher, you know, higher charge storage, charging time, those types of things. Carbon sequestration, where you take CO2 from the air and you're able to come up with a catalyst that converts it to something that's more friendly in materials design. So computational chemistry probably will be ultimately the largest use case for quantum computers in the future. Um, Again, quantum machine learning. We know that quantum that AI requires these really large supercomputers, and people are getting
Hey,
very worried about the amount of energy that's being taken to
doing well, getting educated to think.
quantum quantum language models. So quantum machine learning, if you can use quantum computers to do some of that, that would definitely reduce the electricity use that's used. Finance is a big area. A lot of the finance companies are looking at utilizing quantum computers as early as possible. And the reason for that is because the payoffs can be very large. If you're running a portfolio that's let's say $100 million, and you can come up with 100 basis points or maybe percent worth of improvement, that's a lot of money. So there's a lot of areas where the finance companies think they might be able to use quantum computers. Portfolio optimization is one that's having a lot of research. Currency arbitrage, as you can see in this little picture here on the right, credit scoring, Brexit, impact of Brexit. So financial optimizations is a key area that people are looking at. Logistics and scheduling. Any factory that is scheduling, or anything that has a process where you have to schedule things. A factory that has various machines that's scheduling various jobs that run through that factory. Things like Federal Express, where you're scheduling the delivery of the driver, what the order is, sort of a variant of the traveling salesman problem that I talked about before. Supply chain, how do you pick which suppliers and to minimize cost, to minimize lead times? A very famous one that was written up was at the Port of Los Angeles. Particularly during COVID, when there was a big backup of ships waiting to offload their cargo, how do you optimize the crane movements to take the various cargo containers, move them to the storage yard, and then move the crane containers to trucks that would pick up the containers, then deliver them to their final destination. People developed an application to optimize that, which saved a lot of time, a lot of money, and helped speed up the process of what was happening at that particular port. So logistics is used almost everywhere, even optimizing traffic in a traffic jam. There are experiments that were done to optimize bus schedules, for example. So many areas where quantum computing has potential to create a huge impact. Now let's talk about what some people call bad quantum. So one of the things we use every day is encryption technology, and one of the key areas where we use every day, every time we log into a website, is what's called distributing a key, so we can encrypt our communication. So, for example, if I want to buy something from Amazon and I want to give them my credit card number, I don't want to do that in plain text. But at the same time, I need to use something called asymmetric cryptography. I don't want to drive up to Seattle and hand deliver the key that I would use. I want to come up with something called asymmetric that has a public key and a private key. It turns out that people did not know how to do that until the 1970s when a new algorithm called RSA, or asymmetric cryptography, which had a public key and a private key, was developed. And that really enabled the encryption that we use today, where people can log into a website and they can come up with a way of communicating in an encrypted way with that website without having to physically pass the key. That RSA algorithm was based on a computer science problem of factoring a large number. So if you take a very large number, let's say a number that had 2048 bits in it, and those bits, that number came as a result of multiplying two 1,000-bit prime numbers together. It turns out that the problem of figuring out what those two prime numbers were is what's called a intractable problem. It would take millions and millions and millions of years, even for the very largest supercomputing computer, to figure out what those are. It's called a one-way function. You can take those two prime numbers, multiply them together, and come up with a 2,000-bit of what's called a semi-prime number, but doing the reverse is intractable. But about 30 years ago, about 1995, a researcher at Bell Labs came up, his name was Peter Shor, came up with Shor's algorithm. And Shor said, figure out a way where if you had a large quantum computer, you can indeed factor that or come up with the two factors of that large prime number in a few hours. So all of a sudden, that really kicked off a lot of worries, a lot of investments in quantum computing to be able to do that. But at the same time, it also kicked off a lot of work to figure out ways of correcting that. So you may have seen last week the U.S. National Institute of Standards and Technology, called NIST, had been working on this problem for 5 years with many, many researchers, and they publicized 3 algorithms that used a different computational problem to be able to come up with what's called this asymmetric post-quantum cryptography key that will allow you to do what the RSA algorithm did, but would not be broken by a quantum computer. So there's a big effort right now, and you may have seen it in the popular press, to move the whole IT infrastructure to use these new algorithms. Anyway, this is something that's sort of been in the news, so I'm mentioning it now. There are quantum ways of being able to solve this. The NIST way, what they just said is what's called solution 2, as you can see in this slide here, are these new classical algorithms. It's known as PQC, post quantum cryptography. There's actually a way of using quantum physics to be able to do that, which other people are looking at. It's called QKD, quantum key distribution. And you can send a stream of photons, and using some of those quantum mechanical traits that I was talking about earlier, like the no cloning theorem, you could also prove that that can't be intercepted and broken. So there's a lot of work in this area, but I will mention that eventually quantum technology is not only useful for computing, but you could also use it for a quantum internet. You could also use it for quantum sensing. So there's a lot of potential there. So let me just very, very briefly say who's involved in this. There's a very large group of organizations, and our website, we have them listed under what's called the player section. There are many universities, hundreds of universities around the world that are doing research in quantum computing. There's a large number of government labs. Many of the U.S. Department of Energy labs are working on this, like Brookhaven National Labs and Fermi National Labs, Lawrence Livermore National Labs, Berkeley National Labs, as well as labs in the UK, government labs in Israel. Here's just a quick list of some of the commercial companies that are involved. Many of the large public companies that we know are involved in computing have major quantum efforts going on. IBM is a very large effort that they've been working on for many years, as well as Google, Amazon, Microsoft, Intel. Many of those companies are hosting quantum over the cloud. The abbreviation we use is Quantum Computing as a Service, QCAS, and you can log into some of those systems. There's also a whole variety of startups. The list on the right are what I call newly public companies. Um, the first four of those in those lists are startup companies that have gone public versus via a SPAC transaction, what's called a SPAC transaction. You're familiar with that. And the last one went public through what's called a reverse merger. So you can buy stock in all those companies on this page here. Some of those are startup companies. Um, the startup companies certainly are losing money, but they went public based on the potential of quantum. And then there's hundreds of startup companies, and I've separated those into a few lists. This is hardware companies that are all developing different variations of quantum computers. As I mentioned earlier, there's many ways of building them, and many of these companies are working on different ways. And again, they're around the world. Many of them are in the US and the UK. There's some in Australia, Canada, Israel, as well as in Europe. So it is a world, and China too. So quantum is definitely a worldwide research area. It's not quite as dominated by the US as the early days of classical computing. So this is a list of hardware developers. Here's a list of software developers. I'm sorry, people who are developing specialized software and hardware for what's called control electronics. Um, when someone develops a chip, we call that the bottom of the stack. You have to control the qubits in ways, and those controls are being done by microwaves as well as lasers, which will shine on the qubits and control them to do the various circuit functions. And there are specialized companies that specialize in both the hardware and software that help you control those qubits. And here's a list here. Two of the prominent ones are, again, based in Israel. And then there's people that are developing software at what's called the top of the stack for the use cases and for the algorithms. And again, they're worldwide. They're doing a variety of different things. Many of them have developed what's called SDKs, software development kits. Others have developed specific algorithms for specific use cases. Many of these companies will consult with clients in order to help bring their problem, find a solution for their problem with quantum technology. So, and this is just a sampling of them. There's many more companies. I didn't have time to list them all. We're developing the components like the dilution refrigerator I mentioned, companies developing lasers, companies developing quantum sensors, many, many more that I didn't have time to list them all. Quick note on funding. Funding has been quite large over many, many years. The total amount of funding from governments exceeds $50 billion. China has funded the most, but in Europe and the US and UK, all these countries are funding and continuing to funding quantum technologies and giving grants and some cases just outright buying computers. And that's going to continue for many, many years. Also, quantum venture capital has been involved. Venture capital funding has exceeded $7 billion. Again, you can sort of see it worldwide. These two diagrams, these charts on the left, by the way, are charts that are available to our clients at Global Quantum Intelligence, where we have ways of looking all this data. We have the gigabytes of data, and we have ways of looking at this data and sifting through it and filtering it to give you information about different insights in terms of what's happening. So quantum is well funded, and it's continuing to be funded. In terms of what's happening and when it's going to happen, the way at GQI we look at this is through a variety of eras. Right now, we're sort of in the transitioning into the intermediate era. There are what are called small quantum computers that are available. And the acronym that you'll hear is called NISQ. NISQ, which stands for Noisy Intermediate Scale Quantum, which do not use what's called error correction. And that's a problem because, as I mentioned at the beginning, these qubits are very prone to errors. The external environment will cause them to decohere. So the challenge is for these noisy small scale quantum, can you come up with ways of coming up with some value, some algorithms that have some commercial value? And we're just now transitioning to this intermediate era. But over the next 20 years, the quantum computing will continue to mature in much the same way that early classical computers matured during the 1950s to what we have today. One of the key areas that people will be working on is what's called error correction. And you'll start seeing error corrected quantum computers come up, and they'll make them larger and larger. And ultimately, people will be developing these large quantum computers in, let's say, in the 2030s that will have error correction, that will have millions of qubits. Right now, the largest computer quantum machine out there has about 1,000 qubits. And that's really more of a research machine from IBM. The ones that they're making available to end users have about 130 qubits in them. So there's a lot of scaling that needs to be done. So quantum has a long way to go, but there are various paths that people will take to get there. The size of the market today, right now, there's an organization called the Quantum Economic Development Consortium that every year has sponsored some surveys where one company has surveyed a bunch of quantum providers as well as quantum end users. The estimate right now is that in 2024, the quantum market is about $1 billion, and it's growing at about a 22% growth rate. And the interesting thing is that market is mostly in end users doing proof of concepts or just training. There's very, very little usage of quantum computing in a day-to-day production use. There's maybe a handful of people doing it. But again, that is anticipated. It's going to grow, continue that growth rate of 22%, and ultimately be roughly the size of the supercomputing market which 50 to 100 billion dollars over the next, let's say in the 2030s. So as the technology gets better and better, this market will continue to grow. But that's why people believe that quantum could be the next big thing after AI. Um, Again, it's going to be a multi-billion, tens of billions, or even hundreds of billions of dollar market for the providers, and even more for the end users, who will gain tremendous billions and hundreds of billions of dollars with the benefit due to new products that they can introduce or various cost reductions. So one thing we like to quote is what's called Amara's Law, which is sometimes quoted by Bill Gates, where people tend to overestimate the technology in the short run and underestimate it in the long run. There is a lot of hype, and we try at Global Quantum Intelligence to try to set the expectations, people, that it's not going to be an overnight success. It's still a lot of work that needs to be done, but it definitely has potential for the future. So, to summarize, for people who are interested in quantum, there are a couple of things that we would recommend. For anyone who's involved with IT, we would recommend you take a look at these new NIST algorithms, and you put together a plan right now to upgrade your IT infrastructure to what's called this quantum safe technology, to use some of these algorithms, because there's jeopardy there that if some bad guy, some hacker, could get their hands on a quantum computer and break your cryptography, and it could happen earlier than we anticipate, that it could basically make all your communications transparent, and they can break all your communication and cause tremendous amount of damage. If you're an enterprise, there's probably a lot of potential use cases that you have. And one suggestion from the Boston Consulting Group is that when there is a new technology, that early adopters of that new technology can garner about 90% of the value, at least in the early stages. So there are advantages of being an early adopter. If you're a student and you're looking to try to understand what to major in, or where you'll be able to get a job in the future, one of the things I would point out is that we do anticipate there's going to be a severe shortage of workers in the next few years. It's a new area. Colleges are starting to offer quantum computing classes, but there's going to be a huge demand for workers who are knowledgeable about this area, and you should be able to get a job fairly easily. And even for mid-career professionals, let's say you're been in computer science or computer, there are online quantum tech courses you can take. For example, MIT has some video courses that you can take that will get you up to speed. And we know of people who have been able to transition from a classical company to a quantum company. And then again, if you're an investor, there are some investment opportunities, although you will need a long-term horizon. It's not something that you'll be able to flip in a year or two, but it could, again, be the next big thing after AI. A lot of our work, by the way, at GQI is to help early investors. We do a lot of work, for example, in due diligence. We do that both for investors and for the quantum companies. So there are some opportunities, and you can talk to us. We can show you what some of those are. So with that, just mention that our company does provide a variety of reports, and you can just sort of see the listing we have at that globalqi.com/reports. We have about 15 different reports available. Some of them are available for free, by the way, that talk about various opportunities and what's happening in various ecosystems, as well as in various technologies of quantum. And if you want to know more, you can see there. That's my email address. You can see our websites. globalqi.com is the website for global quantum intelligence. We do have a sort of a free website, quantumcomputingreport.com, that has some of the more recent news. And there's also a free newsletter that you can sign up for at the bottom there. You can see the website at the QCR alert sign up form. So with that, that's what I have to say. I know it's a very brief introduction. We could go on talking for hours and hours about this, but Ellie only gave me 45 minutes for to talk about it. So I'll stop there and we'll take your questions.
Thank you, Doug. If you have any question, feel free to open your mic and ask Doug directly, or you can write your question in the chat and we'll read it out of there. Doug, maybe I'll start with a quick question. So, out of the list from all the actual companies who are already built a quantum computer, who do you think is the most advanced one and the one with the most chance to succeed?
Well, it's sort of like a horse race, and we're only, or maybe a marathon, we're only like at mile number one of a 26-mile marathon. I would say the company that's processing the most right now is IBM. IBM has a very advanced program, and they actually have a fleet of something like 25 systems that they are making available to their end users. And you can go to you just Google IBM Quantum, and you can see that they sell time on those computers. They have a large working with some very large companies um, to investigate quantum technologies. Um, they also have what's called an SDK, software development uh, 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 kit, that you can develop quantum companies, um, quantum programs. So you could try out quantum using IBM. They, I would say, today are the most prolific uh, for a couple of reasons. Number one, they've been offering this to the publics since 2016. Um, they also, of course, have been leveraging their large base of classical computing clients to introduce them to quantum. And then they also have given those stuff a lot away for free. Their software development kit you can download for free, for example. Um, However, IBM right now is focusing on one technology. It's called a superconducting technology. And if you talk to some of these other companies, they believe that you will find that other technologies will ultimately overtake superconducting. So I would point out that um, two of the cloud companies, Amazon Web Services, has an interesting approach. They've partnered with several of these other companies that have other alternative technologies. So you can sign up for an Amazon service called Amazon Braket, Braket, and that allows you to access like 3 or 4 different quantum providers from that list of startups I showed, that you can try out different technologies. And similarly, Microsoft has that. Microsoft has a cloud capability called Microsoft Azure, Azure, where you can do the same thing. You can sign up and you can access several different ones. And others have ways of doing it directly too. So it's still to be determined who's going to be the ultimate winner. There probably actually will, like the classical computing industry, there'll be multiple winners. But like I say, that think about it like the early days of the computer industry, where you had companies like Univac and Burroughs out there that are no longer around, or the semiconductor industries, where the first technologies, first transistor companies, and the largest ones were building transistors out of germanium. So the leadership could change over the years, and it's going to be a long marathon.
Okay, I have a few more questions on the chat. The first one, what is the main difference of quantum computing and post-quantum computing?
Okay, so post-quantum, it's actually post-quantum cryptography. And what that refers to is, again, these software algorithms that are quantum resistant, that allow you to use an encryption code which can't be broken by a quantum computer. But a post-quantum cryptography, PQC, those are all run on classical computers. So those are really classical algorithms that are just quantum safe. And quantum computing and they don't use any of those special physics, quantum mechanical physics things that I talked about earlier. Quantum computing, of course, does use those quantum mechanical physics
Okay,
traits that I talked about earlier.
all right. Then there's another question, actually another few. Um, aren't you afraid that quantum computing trend is losing steam? A few years ago, it was the hottest buzzword in the market. Today, AI, took that spot. Is it 20 to 30 years away, or is it actually happening in the next few years?
So the issue that we've had in the quantum computing amongst the quantum computing community is that unfortunately there is a lot of hype, primarily from people who don't understand it. So they sign on to this and they get the wrong impression, and they say quantum computing is going to change the world. It's going to cure cancer next week, that type of thing. Among the people who understand the technology, including us, we try to, I call it, manage the expectations. It is a challenging and it's a difficult technology, but people are absolutely making a lot of progress. I was talking earlier about IBM having 1,000 qubit machine. When I first started, one of the quantum computing report, one of the very first articles I had was how IBM put a 5 qubit machine out on the web. So they've already grown it by roughly a factor of 200, and it is continuing on. In our work, we see roadmaps from many of these companies. Our prediction is, let's say, within the next five, and what people talk about is this concept of called quantum advantage. When a commercial company will be able to take a problem and run it on a quantum computer and have that quantum computer solve the problem that a classical computer could not do. We believe that quantum advantage, you'll start seeing that a trickle of applications within the next 5 years. And then over the next 15 years, that trickle will grow and grow and grow and really become many. So it's definitely not losing steam. The technical progress has been, really quite impressive. It's actually grown faster than I thought. It's just that there are a handful of people out there who just hyped it too much. Go back to that graph of Amara's law that I showed earlier. Let me go back to that. I like that graph where people tend to hype it. Where do I have it? Graph. No. People tend to hype it, but it will definitely it will definitely be big.
Okay, another question is the Watson IBM use quantum computer?
Watson AI does not use a quantum computer. We actually work quite closely with IBM. Right now, their quantum effort and their Watson effort, um, they are distinct. Watson is purely classical, but what is interesting is we talk about how uh, quantum can help AI, but I should also talk about the reverse, how AI can help quantum. So for some of the things IBM is working on right now is how to use AI techniques to help your quantum computer. How can you use AI to help you design your quantum programs? How can you use AI to actually calibrate the quantum computers and calibrate the that the quantum controls? So um, they can help each other, and I think what you'll see first is how AI techniques can be used to help quantum computers be more powerful.
Another question, will quantum computers be application and market oriented, designated, or multi-purpose?
I think you probably see a little bit of both. Um, there will be some quantum computers that will be specifically tailored for a specific application. Um, versus there will also be general purpose quantum computers. And perhaps the analogy you might use is in the semiconductor market, there are microprocessors which through programming can do all sorts of different programs for all sorts of different applications. And then there's application specific integrated circuits, ASICs, which are only designed to do specific functions. I think you'll see both in the quantum technology market.
Right. Oh, there's one more. How do you see cyber security landscape change from today infrastructure to the new era of quantum computing?
Well, again, that will go back to what I was talking about before with solution one, solution two. Um, there will be a very, very large upgrade to the IT infrastructure to make it quantum safe. And for those of you who remember Y2K, where people had to upgrade their IT infrastructure to handle a 4-digit year, there's something similar. We call it Y2Q, years to quantum. When will these large quantum computers be available to jeopardize the existing code? So again, we're recommending that people start planning now to upgrade their system. And again, the usual assumption for when what's called Q day is going to happen is 2035, but we're always worried about, what I would call a black swan or some brilliant PhD student coming up with a way of breaking those codes earlier than we think. So our, anytime we talk to a chief information officer or a chief security officer is figure out how to do it right now. Um, it's going to be a multi-year effort because encryption is used everywhere in IT. Some of these large enterprises, like a bank, may have thousands of places where they use encryption, and they're going to have to figure out how to upgrade all those various places. So, there are companies out there like Sandbox AQ and QSecure and IBM and many others that will consult and help people do that. But if there's any one immediate thing I would recommend that's a company do to get started with quantum, if they haven't started it yet, is start right now to figure out how to upgrade your IT system. Put a plan together, because implementing that plan could take years to capture all the various places where cryptography can be used.
Right. Another question. Which universities lead in quantum computing programs?
There's many of them. I think many of the universities are working on it. Certainly companies like universities like MIT and Harvard and Berkeley have programs. I actually have a web page um, on the Quantum Computer Report. It's called Universities that have a listing of universities that do research in quantum, but I think I have over 300 again worldwide that are working on them. Many of them, if they don't have it, they're already starting it. But certainly, any university that's already strong in classical computing, I'm sure has a strong quantum computing program also.
Yep, I should mention that the Weizmann Institute of Technology in Israel also have a world-leading quantum research lab, and that's where I think the first Israeli quantum computer was established.
Yeah, yeah, and there's many. There's several universities in Israel that have programs.
Well, Doug, it was a really a great insight into the quantum world. Thank you so much for your time and for enlightening us. This talk will be available on the Mirage Talk website in the recording section. Thanks again, Doug, for your time. And until next week, thank you, everybody. Bye bye.
Okay, thank you. Bye bye.